Hello everyone, I will present our work, 240 FPS stereo vision from monocular mixed spikes. Our goal is to obtain high frame rate stereo video and the corresponding depth results using only one spike camera by combining optical modulation with computational decoupling. Binocular and multi-camera systems usually provide high accuracy, but they also require more complex hardware and generate larger data volumes. Monocular methods are more compact, but they often rely on learned priors, so their generalization to new scenes can be limited. Our idea is to keep the compact single camera setup, optically mix two views first, and then recover the two views from high-speed mixed spikes. Specifically, for the two views, the optical system modulates one optical path and forms a mixed view, which is captured by the camera. Then we use the modulation cues to decouple the two views, output stereo video, and further estimate depth video. Our real optical path system consists of a planar mirror, an LCD modulator, a beam splitter, and a spike camera. These components work together to mix two views onto a single sensor. For clarity, the system can be simplified into a two-dimensional top view. The planar mirror is placed at about 45 degrees. One view travels through the reflected path, while the other view travels through the direct path. The beam splitter combines the two paths on the same sensor, and the LCD modulator changes the transmittance over time to introduce a known temporal modulation cue. In the complete optical path, the right view first passes through the LCD modulator, so its brightness changes over time, and then it is reflected by the planar mirror to the beam splitter. The left view is not modulated, it passes through the beam splitter and merges with the right view to form a mixed view. The spike camera receives this mixed scene and outputs a spike stream. The mirror reflection also introduces a horizontal flip, which is handled later during system calibration. The spike camera continuously converts incoming light at each pixel into photoelectrons. These photoelectrons keep accumulating in a capacitor. When the accumulated electrons exceed the threshold Q, the pixel triggers a spike, outputs a value of 1, and then resets the capacitor. This process can be described by an equation. The accumulated photoelectrons between two spike timestamps are equal to the threshold Q plus a small offset term. The overall method has two stages. In the first stage, we directly perform baseline decoupling from the mixed spikes. In the second stage, SMS-net refines the two reconstructed views, removes residual artifacts, and outputs stereo video. The refined stereo video can then be used for downstream depth estimation. In the first stage, we use a short temporal window to collect spikes and their timestamps. Based on the spike-triggered intervals, we formulate a set of equations and construct a linear system. We then solve this system using least squares optimization. The baseline decoupling is efficient and can already separate the two views, but the result is still not perfect. It may contain brightness inconsistency, cross-view residual artifacts, and texture loss in the modulated view. These problems motivate the second stage, where we use a learning-based network to restore a higher quality stereo pair. SMS-net contains three main modules. The ABC module uses the mixed spike intensity map as brightness consistency guidance. The CBA module applies cross-view attention, allowing the two views to help each other suppress residual artifacts. The RSF module recurrently fuses temporal information to recover details. Finally, a frozen stereo estimator converts the refined stereo pair into disparity and depth. On synthetic data, the baseline decoupling already recovers meaningful left and right videos, while the refinement further improves sharpness and consistency. When the refined stereo pairs are used for depth estimation, the results are close to the upper bound obtained from ground truth stereo inputs. On real data, we observe the same trend. To conclude, we propose a compact monocular system for 240 FPS stereo vision. Temporal optical modulation makes mixed spike decoupling tractable, and the two-stage pipeline reconstructs high-quality stereo video for depth estimation. Thank you for watching. More information is available on our lab homepage.